Okay, so I'm David, and today the topic is about good quantum good quantum LDPC with linear time decoder. And this is a work done with Irit, Dinur, Min-Hsiu, Hsieh, and Thomas Vidick. And so essentially this is like pretty similar topic as the talk we just heard, except that here we'll take a different perspective. So in fact, we'll do something more mathematical and a bit more abstract, and as we'll see soon. So, okay. Yeah, so the first thing is that we're talking about quantum LDPC code, but here we'll take a somewhat mathematical notion. So later on, quantum LDPC code means bounded degree three-term chain complex. And let me first explain this red part, so the three-term chain complex. So a three-term chain complex, okay, contains three vector spaces and generated by three sets, so x0, x1, and x2. So that's a vector space, and then there are two linear maps, delta 0 and delta 1, which compose to 0. So the vector space, linear map, and then this condition is the definition for a three-term chain complex. And these delta maps are called the co-boundary operators, and then if we take the transpose, these partials are called the boundary operators, and they also compose to 0. Yeah. So later on, we'll just do these kind of mathematical notion, but for now I just want to say one thing, like how it's connected to quantum. So in fact, this definition is equivalent to the CSS code we just heard from the last talk. And another connection is that these x0, the sets, correspond to the x stabilizer generators, x1 correspond to each qubits, and x2 corresponds to the z stabilizers. Yeah. And in fact, an important parameter later on, which is the number of physical qubits, is here, which is equals to n. Okay, so that's the only thing I'll talk about quantum. So that's the definition for the quantum code part. For LDPC, this blue part, what it means is that these two linear maps is sparse, meaning that if you write it out as a matrix, there are only constant number of ones on each row and each column. Okay, and the most important parameter for a code is dimension and distance. And again, we'll define this using the language chain complex. So just to remind you, the kernel of a map is the vectors that map to 0. And the image is the set of vectors that can be mapped by something, so mapped by delta 0. And an important relation here is that the image is a subset in the kernel, which is due to this relation in delta. So a vector, okay, so the image of the delta, okay, the vector that's in the image of delta 0, it has to map to 0 after passing through delta 1, and so that's why it's in the kernel. Okay, and from there you can consider the quotient of the two vector spaces, which is defined as the homology. And in fact, the first talk on Monday, also uses this kind of language of homology. Okay, and okay. All right, so the dimension would be the dimension of this homology, which characterizes how much qubit you can store in this system. And for distance, you also have a similar notion using kernel and image, which is the minimum of the x distance and z distance. And for the x distance, you can think of it as a distance that go in the forward direction. So what it is that you consider the vectors that's in the kernel, but not in the image, and you look at the minimum Hamming weight among them. And for DZ, it's the same thing, but you go in the other direction. Okay, and so although the topic is about decoder, but in fact, I won't talk too much about them. So here I just want to tell you that you can also discuss these things using the language of chain complex. All right, so the main question for this paper is that, so first of all, are there quantum LDPC codes with linear dimension and linear distance? And then second, does these code has a linear time decoder? Yeah, and so the first question is also known as whether good quantum LDPC code exists, and that's an important question that's open for a long time until 2021, solved by Palatif and Kalachev. Okay, and so that brings us to the history of quantum LDPC. So the first quantum LDPC code is this Tor code constructed by Kitaev in 1997 1997. And the code has this square root distance. So recall n is the number of physical qubits. So it has square root distance, and the dimension is 2. Soon, this dimension is improved to the optimal values that is linear to n. However, the distance, it's only improved by polylog factor. And this was until 2020 in this fiber bundle code, which really breaks the square root barrier. And soon after, many results follows, and in 2021, Palantir and Kalachev fully resolved this good quant LDPC question. Okay, and after the paper came out, you see there are so many results, following results, and you can see that all of them actually are in 2021 or 2022. So I list out the full number here. So at this moment, besides the original construction, now we have a total of 3 constructions. And we also know that they have linear time sequential decoder and a log time parallel decoder. At the same time, it's worth noting that independent of quantum, there is a work on classical locally testable codes, which turns out its construction shares a lot of similarity with quantum LDPC codes. And in fact, many of our approved techniques actually borrows from this paper. So that's inside coding theory. Outside of coding theory, these construction also has applications. So one application is in some instance for sum of squares, and another one is the one we just heard this morning on the NLTS conjecture. Okay, and all right, yeah. And so since there are so many different results, let me just state the main contribution of this work. So first, we gave a new construction of good quant LDPC codes, which we show that it also has a linear time decoder. And one key lemma that we use is to show that to show the existence of optimal robust tensor codes. Yeah. So for now, I'll just say that you can think of this robust tensor code condition as some kind of GV bounds of for these kind of tensor constructions. Yeah, so these are some concrete results, but I also want to highlight some more conceptual improvements. So first of all is that so this paper gives a simpler proof for this linear distance, which is pretty analogous to how you show these distance property for the classical Tanner constructions, which uses some kind of random walk, these kind of arguments. So additionally, we also try to phrase everything using this language from high-dimensional expander. And high-dimensional expander is essentially a nascent field in combinatorics and TCS, which is also very interesting. And here using these languages, we can conveniently state the results. And in particular, later on, you will hear boundary and small set boundary expansion pretty often. Okay, yeah. So that's the result, and now we'll move on to the construction. Yeah. So although I mentioned there are three constructions, but they all follow a similar strategy. So the strategy is that you would take a K-way graph, which we also heard, and then a tensor code. Afterwards, we'll combine them using the Tanner construction, which would gives us the code we want. And if we use the language of high-dimensional expanders, you can interpret this as, you can replace this robust condition as certain boundary and co-boundary expander. And then together, what you get is a small set boundary and co-boundary expander. Okay, and I'll explain more in detail. But I just want to highlight that this is precisely the condition that's needed to show these complexity results. Okay, and now we'll go into more detail and discuss the three components. Okay, so first is the graph. And so to get the left-right K-way graph, you'll need a group and then two sets of generators. So later on, they will have size delta. From there, you can construct the vertices, edges, and faces. So let's start with the vertices. So here there are 4 groups of vertices. Each group has the vertex labeled by an element in G. So essentially there are 4 copies of G. Okay, and then you have these vertical and horizontal edges. So the vertical edges connects G with AG. And the and the horizontal edge connects G with GB. Okay. And because of the left action and the right action commutes, in fact, they also form squares. So here the squares contains element in G, AG, GB, and AGB. So from the previous talk, so this construction is slightly different from the previous talk, which only has 1 copies of G. But for our proof to work, it's easier to think of it by like separating it into 4 groups. Okay, so one thing I want to also mention is that besides just having 2 sets, they also have to satisfy an expander property. But I won't go into more detail. What I want to say is just that this lambda is characterizing how good the expansion is. So the larger, the better. Okay, so that's one way to think about the graph. Another way to think about the graph is through this local view. So if we take a horizontal edge, GGB, it's connected to, so we can look at what's the neighboring objects. So in this case, it's neighbor to like delta number of faces. And that's because there are delta choices of A. Okay, and then if you instead look at a vertex, then it's connected, it's connected to like delta vertical edges and then delta horizontal edges. So each pair of horizontal and vertical edges forms a square. So that gives you delta faces. And this kind of like this structure, this local view is actually very important for the construction of Tanner codes, and is essentially like how why we need this graph. Okay, so that's the graph, and then now we'll move on to the code. So as I said, robust tensor code is in a high-dimensional language, it's this co-boundary expansion. So let me explain what that is. But before that, I'll actually have to first tell you what the tensor code is. So a tensor code is essentially a tensor product of 2 classical linear codes. So say MA and MB are the generator matrix, then you can use MA and MB to form like these 4 maps, which you can combine them into this chain complex. And that's called MY. So the co-boundary expansion, the condition saying that for every vector, for every purple vector, after this delta 1, it has to expand by a factor of D2. And however, the tricky thing is that it's up to this image here. So delta 0, C0 is an image. So it's only expanding up to some kind of image. Okay. All right. So at first, this condition may sound pretty artificial, but I just want to tell you that this is a very natural and like a correct definition. And let me actually try to convince you by giving an example in one dimension. So in 1 dimension, in fact, this notion is the same as the notion of codistance. And let me explain. And when I talk about 1D, I mean, instead of having 2 linear maps, now there's only 1. So consider it also a generator matrix from this purple vector space to this orange vector space. Then now in this case, there is no green parts. So the condition is simply this one over here. Okay. And actually, I haven't told you that what this norm is. And in order to explain further, I'll have to expand it, explain what it is. So here, for this orange vector, this norm is simply the Hamming weight. For this purple vector, the norm is like a binary value, which is 0 when the vector is 0 and is 1 when the vector is non-zero. So if you expand it, it becomes this condition, which is essentially saying that like the non-zero code word has weight D1, and that's precisely the definition for distance. Okay, So hopefully that has convinced you like why co-boundary expansion could be a natural notion. Okay, and with that definition, we can in fact state the key lemma. And okay, and another notation here. So MA perp is the generator matrix for the dual code. So the key lemma is saying that there exists two classical linear codes of length n equals to delta, such that MA tensor MB and also MN perp tensor MB perp both has this co-boundary expansion. So here you see that a kind of so normally this is stated as two conditions, one for distance and one for robustness. But here, since, as I say, distance is kind of a co-boundary, you can also interpret as a co-boundary. So you can in fact merge these two conditions. And that actually allows us to generalize this notion to higher dimensions, as I'll discuss more at the end. Okay, and here I just want to digress a little bit. So after this, I'll go back and talk about the Tanner construction. But I just want to show you how you could define the small set co-boundary expansion. So at this middle, this is again the definition for co-boundary expansion. What I do now for small sets co-boundary expansion is to simply say that, okay, instead of requiring all vectors to expand, now we only require the short vector to expand, meaning that this expansion only have to hold for vector with small weights. So that's pretty simple, and that's the definition for a small set expansion. So one thing is that this implies distance, linear distance. Okay, essentially this implies everything we pretty much hope for. So for example, distance and also the complexity results. Okay, so now let's go back to the Tanner construction. So now we have the graph and the code, and then we want to now combine them. So the idea of a Tanner construction is that we want to replace a vertex with multiple vertices and each edge with multiple edges. And the way we do that is, first we start with this left-right K-way graph. We look at its local view, which can be organized into this form. So recall that the reason we can organize this into this grid structure is because each vertical edge and each horizontal edge determines a unique square. And so that's why we can organize it this way. So from here, we'll now expand the vertices. So we will replace a vertex with like a grid of vertices and each edge with like multiple edges. So by doing that, we will get these green, red, and these blocks. So the final thing we have to do is to define their incident structure. And this incident structure is given by the code, MA and MB. Yeah. Okay, so that's the Tanner code. This is the Tanner construction. And the next slide, I'll use this same picture, but you should now think of it as the new graph after this Tanner construction. Okay, so with this new graph, we can now construct a chain complex out of it, which is same as defining a code. And this is essentially where like these three construction differs. But let's first focus on the construction in this paper. What we do is that we set the vertices as the x check, the edge as the qubits, and then these faces as the z check. And what's nice about this choice is that it's organized by dimension, meaning that the x0, the sets correspond to 0-dimensional object, x1 correspond to the 1-dimensional object, and x2 correspond to 2-dimensional object. Okay, so, yep. But besides this, so this is the one I just described, but besides that, you can also have other options. So for example, you can put the x check on the blue edges, z check on the red edges, and qubits on the green and the orange. Or you can put qubits on the orange and checks on the green part. So there are different choices. So each of them has their like pros and cons. So for example, the two on the left, they're symmetric, meaning that in terms of proof, now you only have to show in one direction, as we have just heard. But for our construction, since when you try to flip, so when I say symmetric, I mean that if you flip the x and the z, if you exchange x and z, for these two construction, they're still the same same thing. But for us, the 0-dimensional and the 2-dimensional object would switch. So now it becomes a different structure. And so we have to prove the expansion separately. However, there are also some benefits. Since our construction is organized by dimension, it's easier to think about their higher dimensional generalizations. Okay, and so that's the construction. And then I'll just say one thing about the proof. So as I say, there are two parts. For the forward direction, our proof utilized the graph expansion. So this is where we utilize the graph and the code expansion properties. For the reverse direction, actually we don't use them directly. Instead, we reduce this question, the second question, to the first question. And this reduction doesn't use anything too fancy. It's just linear algebra. Okay, so that's essentially the idea of these two parts. Yep. Okay, so the second part is actually a pretty nice proof, which essentially the key idea is you have to reconstruct multiple objects. So here's a animation due to some request from some of the audience. Okay, so you can watch it back home. All right, the point is that yeah, so the point is that you can find the object and then that reduced to the earlier problem. And the same trick also, so I haven't talked anything about the decoder, but essentially it's the same proof. So you don't need any new tools. Okay, and so just to summarize, so we gave a construction that combines the graph and then the code, the tensor code, to get the small set boundary and co-boundary expansion. So from this condition, we can get everything we want, including linear distance, and then these complexity results. So what are some open problems? On the coding theory side, you can think about, okay, can we make these codes have some fault-tolerant properties? And outside of coding theory, you may also wonder, are there other applications? Yeah. The last thing what I want to focus on today is, can we have higher dimensional generalizations? And this is an important question if you're interested in quantum LTC, which is the topic, which is for the next talk. Okay, but here, one hope is that maybe we can combine a 4-dimensional graph with a 4-dimensional code to get quantum LTC. However, there are some issues. So on the graph side, there are some known high-dimensional expanders, but they're not as nice as left-right Cayley graph. And on the code side, we actually don't know if these code exist. And one reason is that in the 2D proof, we use the idea of rank, which doesn't exist in 4D. So that's kind of an obstacle. However, if you solve both questions, then the tools we give in this paper could probably help you to combine them. Essentially, if given some structure, okay, given some assumption about the structure of the graph and the code, our proof do generalize to higher dimensions. Yeah. Okay, and that's it, and thank you.
There's a notion of tensor rank, isn't there? Tensor rank, there is a notion of...
Right. However, okay, one thing I can say is that sort of in 2D, the proof utilized two kind of definition of rank, and somehow in 2D it's the same, so there's no problem, but in higher dimension, they're not the same, so the proof doesn't go through.
Okay, so when you're talking about these expanders, are you like working with LPS expanders if you construct an example? And how does the scaling of the first feasible codes scale compared to other constructions?
So you're talking about more practically how they
Slightly,
differ.
yes.
For that question, you might want to ask Chris.
Oh, even compared to PK? Or like Panteleev and Kalichev's? Or are they like factor of 4 different? Okay, so still tens of thousands to hundreds of thousands. Sound good. Thank you.
So you defined a family of good LDPC codes with number of physical qubits growing like N1, N2, N3, and so on. And what's the ratio what's the ratio of growth? Ni over Ni minus 1. Does this grow polynomially or it's more sparse?
Okay, like because it's a family of
It's a
codes,
family
so
of
you're
codes.
asking how fast.
Yeah.
I see.
How rapid your number of physical qubits grows in your family?
So essentially, all these construction, the thing that grows is the graph.
Yes.
And so back to the graph.
Yes.
I think it's polynomially. I think it's 6 power or something. I don't know. Oh, okay.
Exponential. In terms of number of physical qubits, I mean. Yes. Codesma requires it should be polynomial to have a FTQC protocol. Am I correct? Codesma 2000.
It's sufficient. You'll have to check out.
We can talk later. Yeah. Thank you very much.
Maybe one more, quick, or not so quick. I want to thank the speaker for the comparison slide. Can you flash that again? In the meantime, let's thank the speaker more generally.